Hello everyone, we are Group 3 students from KKM 3223 Fluid Dynamics. Our CFD project title is Vacuum Sensing Hole Effects on Fuel Dispenser Nozzles. Our team are supervised by Prof. IR Dr. Sharil, Don Muhammad AZIM as team leader, and team members are Hoshen, me, and Shamil. Fuel dispenser hole nozzles are critical for safe refilling, relying on a small vacuum sensing hole to detect when a vehicle's fuel tank is full. This hole triggers an automatic shut-off to prevent overfilling. The size of this hole directly influences the strength of the vacuum signal, which control the pressure dynamics inside the nozzles and determine how accurately the shutoff mechanism works. As highlighted, inappropriate hole size may lead to delayed shutoff, causing spills or premature shutoff, reducing efficiency. Our hypothesis for this CFD project is, as the diameter of vacuum sensing hole in a fuel nozzle increases, the pressure change will become less sensitive, potentially leading to slower shutoff response or failure to trigger the shutoff in timely manner. Our first objective is to simulate internal flow characteristics and pressure distribution within the nozzles for different vacuum sensing hole diameter. Second objective is to analyze the effect of vacuum sensing hole diameter effects to pressure changes and shutoff response when being blocked.
And we decided to use venturi tube design since the concept is the same as the vacuum effect in fuel dispenser nozzle shutoff system. And then this is our venturi tube with a sensing hole that we initially set 1.5 mm and 20 mm for each inlet and outlet at the nozzle, also 10 mm diameter throat to create pressure difference. And not to forget that we use volume extract option to enclose all the gap to ensure the proper flow of the fluid. The airflow gap become a CFD domain for us. Then we insert inflation to create fine mesh near walls to capture boundary layer flow, which improve accuracy of velocity and pressure near the sensing hole. After applying inflation layer, the mesh was generated with finer sizing near the sensing hole. Inflation ensure accurate capture of near wall velocity and pressure gradient, essential for modeling vacuum behavior. The final mesh was checked for smoothness and resolution in critical region. A boundary condition were applied to define air entry at the inlet and suction at the outlet. The sensing hole was treated as a pressure outlet during normal operation and changed to a wall to simulate a blockage. This setting replicates a real nozzle behavior under different conditions. We ran 6 CFD simulation, 3 hole sizes which are 1.5, 2.0 and 2.5 mm under 2 conditions, hole open and hole block. In the open hole case, airflow into the nozzle and exit through the sensing hole. This steady state simulation shows baseline vacuum strength. For the block hole case, I switched the sensing hole from outlet to wall at t equal to 0. This transient setup simulates a sudden blockage like when fuel covers the hole. Pressure and velocity contours confirm the venturi effect. Simulation clearly shows air being drawn into the sensing hole. The pressure drop in the sensing hole capture the pressure rise after blockage. I also plot pressure along the venturi to measure the response strength. Smaller holes create stronger vacuum signal and faster shut-off response. Larger holes delay the shut-off, proving that the hole size directly affects nozzle performance.
In all three cases where the sensing hole block, velocity streamline shows smooth, undisturbed flow through the main nozzle. No suction or reverse flow was observed at the sensing hole, confirming that the shut-off mechanism stay inactive when the hole is closed. As the hole diameter increased, only minor difference appeared near the base of the hole, such as slight boundary layer thickening or stagnant soot. For the first picture, in all the plots, it's clear that the pressure is highest at the inlet, shown in red and orange. As the fuel flow into the narrow throat, you can observe that its velocity pick up, and at the same time, the pressure drops significantly, changing the green than blue. This illustrates Bernoulli principle in action. The middle picture shows the velocity contour plot are generated to visualize the venturi effect and ensure the simulation is physically realistic. The all blue contour is the correct result for a velocity plot on a wall surface because of the non-stop slip condition. The pictures of the lab part show the analysis of air suction streamline reveals distinct difference among the three hole size. The 1.5 mm hole shows minimal air influx with only a few thin streamline, while the 2.0 mm.
Hi, I'm DIONG and I'll be presenting the remaining parts of our slides. On this page, it shows the results from scenario B, where we simulated a shut-off event by blocking the sensing hole. On the left is the pressure contour. You can see that the lowest pressure still forms at the throat of the venturi tube, just like what was seen previously in scenario A, open condition. This confirms that the blockage doesn't disrupt the overall flow pattern of our system. Furthermore, on the right side, it shows the velocity streamlines of our simulation for scenario B. You observe that even after the hole is blocked, the maximum velocity values remain similar across all diameters, which also aligns well with the data that we have previously recorded in scenario A. This observation validates that our simulation remains stable and realistic, and the only major changes will happen locally at the sensing hole region, which you can observe in the streamline graph. That's where we further our analysis in the next slide. Now, these graphs compare the pressure changes across the center line of the venturi tube with 2 mm and 2.5 mm sensing hole diameters. You can see that the 2.5 mm hole experiences a sharper and deeper pressure drop at the throat region compared to the 2 mm sensing hole. This tells us that the larger hole pulls a stronger vacuum, which is represented in the middle region of the x-axis of both graphs, whereby the 2 mm diameter recorded a pressure of negative 925 pascals, while the 2.5 mm hole recorded a pressure of negative 950 pascals. In practical terms, this means that the 2.5 mm hole could potentially trigger the shut-off faster, but this stronger suction might also make it more prone to unstable or premature shut-offs, especially if there's fuel turbulences or splashing inside the tank. Hence, for the scope of our project, we determined that a smaller diameter of the sensing hole is more suitable to be used in fuel pump nozzles, as in the real world, at gas stations, if premature shut-offs occur, it may greatly inconvenience users and reduce fuel dispensing efficiency. So in conclusion, we found that the sensing hole diameter has a direct impact on vacuum strength. Larger holes generate stronger suctions. Seen through more negative pressure and higher flow velocities, the 2.5 mm hole showed the strongest response. However, this also introduces a trade-off. While faster vacuum formation improves shut-off sensitivity, too much suction may cause inconsistent or early shut-off events. Therefore, the sensing hole size must be carefully optimized in design, not just for sensitivity, but also for overall reliability on the fuel dispensing system. And that brings us to the end of our presentation today. We hope that our presentation was insightful and informative. Thank you for your attention and thank you for watching.